So hopefully everything will go smoothly. Certainly looking forward to sharing some information about SolidFire with you and getting to answer your questions. So as Jay mentioned, the goal today is really to give some background on the SolidFire technology and architecture and what we're trying to do and where we're focused here and the problems that we're solving and perhaps how we can help you build a better cloud with more mission-critical applications. So if you look back to where SolidFire started from, the genesis of it was really my time at Rackspace before I started SolidFire, and the desire to allow the cloud to host more mission-critical, high-profile applications. And storage was always a big stumbling block. It was one of the things that made it very difficult to host applications that were traditionally hosted in dedicated data centers or on dedicated hardware. Putting them in a shared multi-tenant infrastructure with shared storage was very difficult. And I think if you look at what primary storage in the cloud looks like today, if you look actually under the covers at the type of systems that people are putting in place for primary storage using traditional enterprise storage systems right now, it's kind of an ugly picture. This is a kind of well-known cloud-in-a-box configuration from some of the leading enterprise software and storage vendors out there. And I think when I first saw this, the thing that shocked me the most was that the storage is such a huge part of the footprint from a size perspective, from a cost perspective, from a power and cooling perspective. In order to get enough horsepower to serve the applications that you can fit in a dense compute environment, particularly a very dense kind of blade compute environment like this, you need a tremendous amount of storage capacity and performance to be able to do that. And the challenge there is that as you scale out a data center, particularly a cloud-scale data center, you end up with a footprint that is dominated by storage rather than compute. And while certainly storage is important, when you really look at where the revenue is being generated and where customers are deriving value, it's based on the number of applications and the types of applications that they can run. And so in a moderate-sized data center, you can end up with a significant portion of your footprint, power, and cooling being taken up by storage if you use a traditional storage system in that environment. And really, based on kind of that view of the world, I really thought that there was simply a need for a better storage system, a better type of approach to storage for cloud computing environments, and that was really the genesis for SolidFire, dropping out the big enterprise storage system and put in a system that is much more suitable for the type of environment that we're running in the cloud, for the types of applications that we're running there, for the density of compute resources that you have there, be able to put in something with a much smaller footprint, much lower cost, much lower power and cooling requirements, but significantly better performance. And so that was really the goal for SolidFire, was to replace the big iron storage systems with something that is much more scalable, reliable, and performant for cloud computing environments. And what that really translates to is taking that data center that was dominated by storage from a cost and a space and power and cooling perspective, and putting in a storage footprint that's much smaller, much more power efficient, has significantly greater performance and significantly greater capacity in a small footprint, and allowing you to use the rest of that space to put in more compute capacity, and taking that data center and increasing the amount of usable compute capacity that you can fit in it for, at the end of the day, a similar capital cost and power utilization footprint as what you would have, and simply make it a much more powerful and cost-effective and profitable service. So just with kind of that as a background for why we're doing this and why we think this is necessary, I want to just break down where SolidFire is focused, because I think that's very important. SolidFire is exclusively focused on serving the storage needs of the cloud service provider and the hosting space. We are right now exclusively selling to service providers and just looking at places that have very large-scale cloud computing environments that need this type of storage. Because at the end of the day, if your cloud fits in 3 racks, it really doesn't matter how inefficient your storage solution is, but when your cloud is data center or multi-data center size, it's extremely important, and that's where we can have the most impact with our technology. Now, when you look across the spectrum of the types of storage that are used in cloud and service provider environments today, we kind of break them up into three different areas just to make it very clear where SolidFire is focused. And in particular, a lot of what is thought of as cloud storage today is kind of this middle group here, this bulk object storage section, and this is the Amazon S3 and Rackspace Cloud Files and Nirvanix type of capacity-oriented storage that's really all about lots of cheap capacity and backup and archival and content distribution type applications. But that's not where we're focused. We are very focused on high-performance primary storage in a cloud environment. So when you've got VM images and applications and databases that need to run in that cloud environment, we are focused on being the primary storage for those types of applications. That is the space that we're playing in. And thinking specifically about those types of applications in that space and what the challenges are of serving particularly business-critical applications in that environment, there's really three big things that we've identified, and from my experience at Rackspace as well as our conversations with other service providers. And the three big areas that we are focused on improving are, first and foremost, is really performance. And when we think about performance, there's really kind of two issues there. One is how can you get enough performance to serve the applications that you need without having that kind of sprawling storage footprint that we looked at. But then how can you give consistent, reliable performance to every application in a multi-tenant environment? And I think that's where pretty much any storage system today, no matter what technology it's based on, really struggles, is guaranteeing consistent performance even with a large number of tenants, a large number of applications all sharing the same storage system, because at the end of the day, that's what customers really want before they can trust a cloud environment with their mission-critical application. They want SLAs around storage performance. They want to know what they can expect, and they want to make sure that they're not going to be impacted by what else is going on in that cloud. The second thing we're really focused on is efficiency and utilization, and the reason that that's so important in a cloud environment is because that, at the end of the day, for a service provider, drops right to the bottom line and really drives the ROI. And traditional disk-based storage systems are very difficult to utilize anywhere near their full capacity, primarily because of some of those performance issues that we've talked about. Efficiency technologies like compression or deduplication either aren't available or really just can't be turned on because they really don't give usable capacity, because you end up being limited by performance to begin with, and they tend to make performance worse. And so addressing this challenge of inefficient use of capacity and kind of sprawling storage footprint is a huge part of what we're focused on. And the last piece is the management piece. And you know, with traditional enterprise storage systems being sold into service providers and cloud environments, you end up with the same enterprise management tools as well. And those tools we found are not designed for the type of management the service providers want to do. And specifically, they're really not designed for automation, first and foremost. And that is obviously the key to growing these environments to scale and managing them at scale is automation, and not simply having a lot of administrators with a lot of administrator tools. And so those are the three big areas that SolidFire is focused on. And if you look at the service, if you look at the solution that we're delivering to address that, and I'm sure many of you have kind of looked through our website and seen some of the information about it, I want to just go through a couple of the key aspects of it here. So the first is that it's a scale-out storage system. And what that means is that you can start with a small number of these 1U storage nodes that have compute and storage and memory and networking in them, and add both more capacity and more performance as you scale. So rather than having a kind of traditional monolithic controller and disk shelf design where you're limited simply based on the performance of the controller, each node that you add to the storage cluster gives you more capacity and more performance, up to around 100 nodes and about a petabyte of usable space. But you can simply size the cluster to the capacity and performance requirements that you have, and if you need more, add more as you need it. We use industry standard hardware. There's no real proprietary hardware as part of the solution. That's an important factor in keeping the cost low, as well as giving us kind of maximum flexibility to work in different environments with different types of systems as necessary. We haven't invested a huge amount of our engineering dollars in custom hardware. All of our intelligence is really in really smart, really amazing software. The nodes are connected with both each other as well as the compute environment with 10 gigabit Ethernet, and we use the iSCSI block-based protocol to communicate with the nodes. Some people are kind of curious about kind of use of iSCSI versus NFS or a file-based protocol for a cloud environment like this. And really what it comes down to at the end of the day, if you look at what service providers are typically exposing to their customers, they're not typically exposing a file system to them. They're exposing a virtual disk. They're exposing a block device. And therefore, we thought it really made the most sense to have a storage system that is natively a block-based storage system and is designed to export block devices to the virtual environment. And so that's what we've done, and we've removed a lot of the limitations around traditional block-based storage systems, limitations like the number of LUNs you can have, the number of snapshots you can have, the number of initiators you can configure, the number of hosts that can be connected to the system. Those types of limitations that have often pushed people in large environments to move to file-based storage solutions are completely gone, and really the system functions very, very well as a native block-based storage system for a virtual environment. As many of you probably know, the system is all solid state. We don't use any spinning disks in the system whatsoever. And the use of solid state was really driven by two things. One was to get the performance necessary to serve a large number of applications. And certainly with disk-based systems, that's just a huge challenge. You have to throw a lot of disks at the problem before you can get enough IOPS to serve a reasonable number of applications. Having solid state gives us the right balance of performance and capacity. The other big benefit from solid state is lower power utilization, less power and cooling that's needed for the solution, and one that I think is fairly surprising to people, which is its higher density. In the solution, even as it is today, we have a higher storage density than many disk-based solutions, and if you look at where solid state is going in the future and where the drive capacities for solid state is going, you're actually going to see significantly higher storage density with solid state in the years to come than you would be with disk. And that I think is surprising to a lot of people, but is certainly one of the benefits that we're taking advantage of. But I think the last bullet on here is the thing that's most interesting to people, which is that unlike many solid-state storage systems that were really designed for performance and performance at any cost, we designed our system to have the right balance of performance and capacity, and using really smart techniques to drive the cost down to a point where we can be at a cost per gigabyte that is comparable, if not less than many disk-based storage solutions today. And so in many cases, we can come in with a solution that has a lower capital cost per gigabyte out of the gate that can be scaled in smaller, more incremental steps to keep utilization higher, and then we'll have lower operational costs over time through both lower power, cooling, and space costs, as well as lower operational costs through administration and management. And we're going to walk through in much more detail as part of this presentation the techniques and the ways that we get to some of those numbers. But first I want to spend a little bit more time on the performance question and what SolidFire is doing to kind of bridge this performance gap and address the challenges of storage performance in a multi-tenant environment, because I think this is the thing that has really resonated most with the customers we've talked to, and is certainly one of their biggest challenges. How do I put a lot of customers in a very dense footprint and yet still give them not just good performance but very consistent, reliable performance day in and day out? And that is really what we focused on first and foremost at SolidFire. We've got a lot of raw performance. Certainly the use of SSDs gives us that. We've got about 50,000 IOPS per node, scaling up to about 5 million IOPS in a single cluster. But the real key part of our technology is something that we call performance virtualization. And what this is, it's the capability to separate performance from capacity in the storage system and have two separate pools of resources there that you can dial in individually for every single volume in the system, allowing you to create a volume that has the exact amount of performance and the exact amount of capacity you need without those two being linked together. So you can have large volumes with a modest amount of performance or small volumes with a very high amount of performance. And then the key capability is that you can actually dial up and down that performance for an individual volume in real time whenever you want. Without actually having to physically move or tier data around in the storage system. We've actually virtualized the performance in such a way that if you've got that performance dialed down, you're not wasting that performance. The IOPS that volume isn't using are available for other volumes in the system. If you've got it dialed up, that volume is getting the performance that it needs, but again, you're not wasting storage, you're not short-stroking drives or having to throw more drives at the problem. So within the bounds of what the system is capable of, you have a lot of flexibility to dial in the exact performance and capacity that each tenant needs, and then the system will work to guarantee that performance over time, and I'll talk more about exactly how that functions. But that capability, when translated into a product offering for a service provider, really provides some interesting possibilities. So certainly the most obvious one is that you can now have different levels or tiers of storage performance that are available for purchase and have different prices associated with that, and then have the ability for customers to easily move up and down between those tiers as necessary. And in particular, we provide the data that you can feed into either your sales teams or your customer-facing dashboards that let them know that, hey, you're bumping up against the performance limits of the storage that you're on, and you can easily upgrade or increase your storage performance, and it's completely non-disruptive, and it happens in real time, and you get that performance, and it's very, very visible to you. And that's a huge contrast to the typical experience with primary storage in the cloud, which is that it's a best effort service. You're going to put your application on there, you're going to measure and see what kind of performance you get, but that performance can vary from day to day, week to week, month to month as other customers come on and off of that system. And at any given time, you don't really know what to expect. And really the only knobs that service providers have to turn to get customers better performance is to simply move them onto less lightly loaded storage systems or move them onto faster disks or storage systems that might have solid-state disks or something like that in them. But there's kind of very rough and difficult steps that they can take as opposed to kind of a seamless, very fine-grained approach to storage performance management that we have here. The last piece on this slide about our data protection I think is important to touch on here. We're not going to go super deep into our data protection technology as part of this discussion, but the SolidFire Helix data protection technology was obviously designed to keep data safe and to provide high availability, which is critical in a service provider environment. But it was also designed to manage failures in such a way that they would have a minimal impact on performance. That's certainly one of the big challenges with traditional RAID-based protection mechanisms is that when a failure occurs and when a rebuild needs to occur from a RAID failure, there can be an extended period, a multi-hour or multi-day period of substandard performance and often very significantly reduced performance while that rebuild is going on. And now you have both a large window of kind of additional failures that could cause data unavailability or data loss, as well as a long period where you can have substandard performance. And we've designed our data availability mechanism using a distributed replication-based approach that allows us to rebuild from failures very, very quickly and with a minimal impact on performance. And we're able to do that because we distribute the rebuild process throughout the entire storage cluster rather than having a bottleneck of a single spare drive or a single spare node that ends up as a choke point for rebuilding when a failure occurs. We can use a swarming approach that increases the speed that we can do rebuilds, allows us to rebuild within a few seconds or minutes, and allows us to do it in the background with minimal impact on the other I/O that's going on there. And that's a key part of our performance picture, is being able to consistently deliver those performance levels even in light of failures. So I want to take a little bit of a view at how the quality of service technology that we have works in practice, how you actually dial in that performance and what it looks like to a customer. Dial in quality of service for an individual volume in the system, and that can be done using our APIs or using the management tools that we provide. Those quality of service controls are applied to both IOPS and bandwidth. We'll use an illustration here where we're looking at IOPS. but basically the way that it works is for each volume in the system, you can configure the minimum, maximum, and burst IOPS value for that volume. And the use of those three values is very important. Rather than having a kind of a single target IOPS value, we found that this approach gives both more flexibility to how you can how you serve your customers, as well as better overall performance for the customers and for the storage system. And so the way that this works is, again, we've got three values here. The maximum value is really the target level of performance for that volume. That is the level of performance that our storage system will attempt to deliver all of the time, so long as the actual application is requesting that many IOPS or trying to drive that many IOPS, and as long as there is sufficient performance available in the storage system to drive it, we will consistently deliver that max IOPS level. And we think that the storage system is balanced in such a way that for most customers, they will not run into kind of performance issues before they have exhausted capacity, and so they're unlikely to see a lot of deviations from that maximum. However, if you do get into a situation where customers are really pushing the system hard, or the system has been over-provisioned to the extent that we can't deliver the maximum to every single customer in the system, what the system will then do is scale the target performance level from the maximum down to the minimum. And it will scale that gradually over time as the load continues to increase, and in doing so, scale back the load so that you don't have the kind of large spikes of latency or other issues that can occur as storage systems typically get overloaded. It scales it back in a very graceful manner. But the other thing to realize is that it scales it back proportionally to the distance between the maximum and the minimum. And what that allows you to do is to have customers that are in essence higher priority or lower priority. You can have some customers who may have a very high maximum but get scaled back very rapidly and very dramatically when performance needs to be conserved. Or you can have other customers who the maximum and minimum are within a tighter bound, and they will have less scaling that occurs when performance is needed, and other customers will get scaled back first. And so there's a number of different ways that you can use that maximum and minimum functionality to give different guarantees and different SLAs to different classes of customers, or customers that are buying different classes of storage within the same storage system. So the last value on here that we're showing is the burst value, and this is a third configuration value for each volume in the system, where you can determine if a customer is, if performance is available in the system and a customer has not been running at their maximum for a period of time, we will allow them to burst up to a higher burst limit for a short period of time. And the reason for this is that if you look at most storage workloads in the real world, they're not a steady state workload. They tend to be very bursty. If you think about things like database checkpoints or web page hits or database queries that are going on, those things tend to cause a burst or a spike in I/O activity, and so over time you may be running at a very modest level, but occasionally you'll have these bursts of activities. And if we simply had a hard cap on the maximum, that would cause those bursts to degrade performance significantly, and you would see overall impact to response times, database commit times, and things like that. And so by allowing you to have some flexibility and allowing you to have this bursting capability, you can give consistently good performance without worrying about individual customers abusing the system or abusing that capability and running consistently above their maximum. So we're going to show a little illustration of what that looks like in practice. The blue line here represents the IOPS that the client is performing, or the virtual machine is performing in this case. And what we see with these kind of purple bars here is what we call the credits that it's accumulating. And the credits are used as part of the bursting mechanism. We see the client initially starting out here running at 100 IOPS, which is its configured maximum, and then it drops its I/O load under that. And in this case, it's not because the system is overloaded, but just because it's not requesting more than that number of IOPS. And you'll see as it dips under that maximum, it begins to accumulate credits, as indicated by these bars here. And then as it kind of progresses here, it has a burst of activity. So perhaps a file scan is being done or something like that causes a burst of I/O activity. And what you're seeing is we actually will allow the IOPS on that volume to exceed the maximum and go up to this burst level. But as it exceeds that maximum and runs at that burst, it will consume these credits. And once those credits that it's accumulated have been consumed, it will be locked back down to its maximum. So again, it will not be able to kind of continuously abuse the system by running at that burst. Even if the system has performance available, it will, over the long run, stay within that maximum. Now, certainly if you saw a volume that was always running at the maximum, that would be a pretty clear indicator that that application was being bottlenecked by the storage, and it would certainly be a good opportunity to upsell the customer to a higher level of performance and be able to move that maximum from, say, 100 up to 200 or 300 or 400 or wherever you need to go to in order to make that application a little bit happier and give better performance. But you've got a lot of flexibility here with the minimum, maximum, and burst to be able to deliver different levels of performance. So now I want to dig a little bit further into the topic of storage efficiency. And for us, the efficiency piece is, as I mentioned, extremely important because this is what, at the end of the day, drives the ability to get a very good ROI on the storage system and to make storage something that can be a profit center as opposed to the cost center that it is in a lot of service provider environments today. And really the operational savings that we drive comes through two main things. One is the ability to run the system at very high levels of utilization, and that ability comes through a couple of different aspects of the system. One is that by having the correct balance of performance and capacity, by having enough performance so that you're not being limited by performance, you can actually use more of that capacity that you're purchasing. And that's one of the big challenges with storage systems today is you end up having to purchase far more capacity than you'll ever be able to utilize simply to get enough performance. So having the right balance of performance and capacity allows us to drive high levels of utilization. The other thing that allows us to do that is the scale-out nature of the storage system. So rather than having to buy a very expensive controller and either fully populate it with disks that have a very low level of utilization for a long period of time, or have to add disk shelves as you grow but still have to buy the controller up front, with our storage system you can simply add incremental storage nodes as you need more capacity in a more managed fashion and allow you to run the system at higher levels of utilization and add to it more incrementally. So both of those things allow the SolidFire system to be driven and run at much higher levels of utilization, 80 or 85% utilization, compared to what you would get with a traditional disk-based storage system. However, we go really far beyond just looking at utilization. We actually look at how can we get much more efficiency through data reduction techniques, and we've designed into the core of the architecture the ability to do real-time deduplication, compression, thin provisioning across the entire storage cluster in real time without performance impact. And that's a pretty amazing capability when you look at the benefits that it provides and that it can provide these benefits at essentially no significant cost in terms of kind of performance to the system. So you can get savings from deduplication, compression, and these are not things that you have to trade performance or capacity on. You just always get these capabilities. And the capability to do these things in real time on a primary storage system is really driven by two things. One is that the architecture of the system, being a scale-out architecture, has significantly more CPU power in it, significantly more processing power available in it than a traditional storage system would. In a traditional storage system, you may have say a 4-core processor in a controller, but then you've got 200, 300, 400 disks potentially hanging off of that, all trying to drive I/O through that controller. And there's very little that the controller can actually do to touch or manage the data as it passes through that storage system. It simply doesn't have enough processing power to do that. With our storage system, we've got 12 cores in each 1U box, 10 SSDs in each box. We actually have a ratio greater than 1 core to 1 disk, and so we have a significantly higher amount of processing power available to do things like deduplication and compression in real time. The other thing that really drives this capability is the SSDs themselves. Techniques like deduplication have traditionally been very, very bad for performance on disk-based systems because they end up chopping up the data and spreading it out over a much wider footprint, which with a disk-based system and the seek times that are involved can significantly reduce performance. With our architecture and with an SSD-based system, we can actually use that dispersion to increase performance rather than decrease it. Because we don't have seek times to be concerned about, and because the SSDs have multiple channels, spreading the data out across many disks in the entire cluster allows us to increase performance while still being able to do the deduplication and compression that we need to do. And the net result of all of this is that you end up with this drastic reduction in power, cooling, and floor space compared to a traditional disk-based system, which is what we kind of illustrated up at the start. So that's really all driven and all delivered as part of the efficiency technology that we're focused on. And I want to run through a little illustration of how we think about the efficiency technologies and the types of savings that they can drive. And so we're going to run through an illustration that starts with a kind of hypothetical 100 terabytes of provision space that we've gone out and sold to customers. Now, of that space that has been sold to customers, and again, typically primary storage, block-based storage is sold in kind of fixed capacity increments. And of that 100 terabytes that you've gone out and sold, some percentage of that space will be used immediately, some percentage of it will be used over time, and some will probably never be consumed. And so technologies like thin provisioning can come in and provide us some savings based on what space is actually being utilized by data. Now, a typical thin provisioning algorithm will certainly get you some savings off of that. The thin provisioning algorithms that SolidFire uses are actually quite a bit more advanced than traditional storage array thin provisioning algorithms. And that really comes from the architecture of the system, our ability to address very small discrete blocks of data, and our ability to very, very optimally manage the space that is used versus not used in the system. And one example of that would be that if an application initializes a large file, say a SQL Server database is created and a large amount of space is initialized for that, traditionally a storage system would see those writes that's being done as part of the formatting or initialization process and allocate space for that, and that space would then forever be consumed as part of that, even if no data had been written to it other than the initial initialization that was done. The SolidFire system can actually see that, can determine that that data that's being initialized there is something that can be compressed or deduplicated away or hidden as part of the thin provisioning, and we won't actually allocate any space for that until real actual data is written. And so with SolidFire you can get some additional savings from thin provisioning than you would see with a traditional storage system. Sorry, the presentation's kind of jumping around here. Now, with most storage systems, that's really as far as you can go, is thin provisioning. The few storage systems that have additional efficiency features really tend to not be things that can be used for primary storage. But with SolidFire, that's really just where we're getting started. So we take, in this case, the 50 terabytes of utilized space that's been thin provisioned, and we compress it. And we can typically get around 2-to-1 compression across a pretty wide range of data. After the compression is done, we deduplicate it, and again, the range of deduplication that you can get there certainly varies depending on the type of data that's being stored, but 2-to-1 reduction in deduplication is pretty typical or pretty straightforward to achieve, again, because we're able to deduplicate across the entire storage cluster. And so now we've reduced that 100 terabytes of provision space down to about 12 terabytes of space that is actually utilized. Now that's not the whole story, of course. That's not to say that you can just go out and buy 12 terabytes of space. There are other things that you have to actually take into account. And so now we want to look at that kind of perspective, which is what are you utilizing versus what you're having to purchase. And we'll show that both with a traditional disk-based system as well as the SolidFire system. So with the traditional SAN, again, we've got that 60 terabytes of space that we've thin provisioned that we're utilizing. You've got to add your redundancy on top of that. We find RAID 10 is very common in this space because of the performance benefits over RAID 5 or RAID 6. Depending on the storage system, you may have some system space or snapshot reserve space that is allocated but isn't actually used for real data. And then really the big question with a disk-based system, which is what's your utilization going to be? How much space are you going to have to purchase that you're not actually consuming simply to get the performance you need? And obviously that can vary depending on the storage system, the workload, the types of drives, whether tiering or other technologies are used, etc. But at the end of the day, for that 100 terabytes of space that's been provisioned or sold out there, you've got anywhere from 120 to 360 terabytes or more that's needing to be purchased. With SolidFire, we've got the 12 terabytes of space that we've compressed and deduplicated. We've got the overhead from our redundancy from the SolidFire Helix technology, which is configurable, but is typically around 2x in a normal configuration. We don't have any snapshot reserve or system space that is set aside. And while we're certainly not going to claim you can run it at 100% utilization, we do think you can run the system at much higher levels of utilization than a disk-based system. So there's a relatively small amount of underutilized space that will be there. The net result is that for that 100 terabytes that we've provisioned and sold, we're now only having to purchase between 25 or 30 terabytes of raw capacity, and you've got anywhere from a 5 to 11x reduction in space that you need to purchase, power, cool, etc. And so that is really kind of how we look at the efficiency playing out in practice in service provider environments. Now, we certainly get a lot of questions about this. Obviously a lot of the value that we derive here is through the efficiency technologies and using them to drive down that cost per gigabyte. And so we do get a lot of questions about how realistic are those projections, how realistic are your assumptions in that area about the types of savings that you can provide. And so what we've done is developed a tool that we call the efficiency scanner, or e-scanner. And this is a tool that customers or prospective customers can use in their environment to measure the amount of savings that can be provided with our efficiency technologies. And this is simply a command line tool. It runs on pretty much any Linux machine that you can run against existing data and data sets that you have in your environment. It will scan them in a read-only mode. It uses the same algorithms that our storage system uses and will be able to compute how much effective savings you can get from thin provisioning, compression, deduplication, and overall savings, and be able to give you the actual results of that without actually having to put a storage system in place to move data to a different storage system or anything like that. So you can actually see for your environment, for your data sets, what type of savings you can expect, and you can look at both individual volumes and individual data sets as well as combined runs over multiple data sets to allow you to see the additional efficiencies that can be gained through deduplication as you put more and more data onto the storage system. And this is something that we've shared already with a number of our early access partners, but we're actually going to be launching this publicly starting today on solidfire.com. You'll be able to sign up and download it. And this tool will allow you to, again, evaluate the efficiency gains that SolidFire can deliver for your own storage environment. So the next thing I want to address is the management piece. And when I talked about this up front, really talked about the differences between how enterprises manage storage versus how service providers want to manage storage. And to me, the biggest way to explain it is that enterprises want to administer their storage and service providers want to automate their storage. And so we've really designed the storage system from the ground up to be very easy to automate first and foremost and make sure that absolutely everything that can be done with the system can be done in an automated fashion. And so at the core of the system, we've built a very easy to use REST-based API, something that can be programmed from pretty much any programming environment that you might have out there to allow you to automate any aspect of the system from initial storage system deployment, adding of capacity to the storage system, day-to-day provisioning and deprovisioning, security, reporting, billing, really anything that you could do with the storage system can be done through this API. And while we've built some of our own management tools, we've built CLI and web-based management tools and reporting tools, those tools have all been built on top of this API. And the goal there and the benefit there is to allow a service provider to have a set of tools out of the box that are fully functional and work and allow you to get up and running very quickly, but allow you to, over time, automate more and more of what you do, rely less on the tools we provide, and allow you to integrate more and more of the operations into your workflow, into your tool sets, and into your management stacks. We're also doing the work up front to integrate the storage system into some of the common cloud management platforms that we see being adopted out there. So in particular, VMware vCloud as well as OpenStack are places that we're looking to integrate these APIs out of the box to remove the need to even do any of that work for service providers that are using those platforms. At the end of the day, the goal here is to have storage systems that are as easy to deploy and manage as compute. Easy in the sense that you can literally take a storage system out of a box, plug it in a rack, put a network cable in the back, and never have an administrator touch that system, have everything managed through the existing orchestration, automation, provisioning frameworks that you use, and through the APIs that we provide. That is ultimately the goal as we see the management of the system. So we're getting close to the end here, and we're going to open it up for some questions. I see there are some questions that have been queued up, and I want to make sure we get a chance to answer those. But before we do that, I just want to cover kind of a look at the feature set that's in the product, just to make sure that it's clear what capabilities we're providing out of the box and what is and isn't there. And it's a pretty comprehensive feature set. So in terms of storage protocols, right now it's just standardized SCSI over 10 gigabit Ethernet. We're certainly open to discussions around other block-based storage protocols, but certainly we think that the direction that storage is headed in large-scale cloud-type environments is going to be Ethernet-based, and right now that means iSCSI. And so we've done a very good iSCSI implementation, and we think that's going to be appropriate for most environments. The quality of service capabilities that we talked about, the ability to have per volume IOPS and bandwidth controls, to be able to dial those in at a very fine level and have them enforced by the storage system. Of course, non-disruptive expansion as well as software upgrades for the system. It was designed to run in 24/7 service provider environments and designed to be managed and upgraded in a ongoing kind of rolling fashion. Very space-efficient snapshot and cloning capabilities. And again, this is really kind of a key feature that a lot of storage systems have, but end up putting a lot of handcuffs around in a service provider environment, either because they put arbitrary limitations on the number of snapshots for a volume or for a storage system, or because they have an undue performance penalty that occurs when you use those features. In our storage system, we have no fixed limit to the number of snapshots or clones you can take, and there's absolutely no performance penalty either from taking the snapshot or from running I/O against either the original data or the snapshot. We don't use read, copy, modify, or redirect on write techniques that can affect performance for doing our snapshots. We use a very thin metadata-based approach for doing that. We've got some really interesting built-in backup and restore functionality that, again, is tied into the snapshot capabilities to be able to do point-in-time backups to other storage systems. And in particular, these features have been designed in such a way to make them very easy to integrate with other object-based storage systems like we see deployed in cloud environments. So we can actually have our storage system talk directly to over an HTTP API to another storage system to push and pull data between the storage systems. And this obviously makes it very easy to allow you to have customer control over backups and restores, to do automated backup and restores, and to do them non-disruptively to the other activity on the system, and do it without having a single backup server or a set of backup servers that you have to manage that are kind of pulling the data from one system and pushing it into another. We can push and pull directly into other storage systems. The efficiency feature set we talked about is, we think pretty much unmatched in the industry. The ability to do the thin provisioning, deduplication, and compression in real time across the entire storage cluster without performance penalties. And the last piece on the list, which is remote replication. So the system has high availability within a storage cluster today, but for customers who are looking at having the ability to do off-site remote replicas, either synchronous or asynchronous, that is functionality that we are planning on implementing and will be in not necessarily the GA release, but the first release after that is the plan right now. And again, making use of the compression deduplication capabilities that are native to the system to make that replication be very, very efficient. So when you look at some of the things that we're doing to enable deployment of business-critical applications to the cloud, it really comes down to a couple of things. First is allowing you to manage at a very fine level the performance around storage and deliver it in a very predictable fashion, and in a fashion that frankly is probably more predictable and more consistent than a lot of customers are seeing on their dedicated storage environments today. The ability to have multiple levels of performance and multiple performance tiers around that so that customers can get the level of performance that they need and that they're comfortable paying for. And they allow them the ability to change that performance on the fly, so allow them to kind of ensure themselves that they're not going to outgrow your cloud if their application starts generating more traffic, or if they get busier, they can simply upgrade to a higher tier of performance and get that delivered immediately. And again, that's a capability that most people don't have even in dedicated environments today. Once they've maxed out their storage system, they're looking at a forklift upgrade to get to something bigger. Having this flexibility is something that will not just enable business-critical applications, but make a better experience in the cloud than what people have in dedicated environments today. The other things that we enable here are really all about enabling you to run a better business around storage and critical applications in the cloud, allowing you to use a larger percentage of your capacity to increase your ROI on the system, have significant efficiencies that are gained on top of that through the data reduction technologies we use, and really just manage expectations around storage for the first time. We think is a particularly important way to think about what we're enabling here. So just want to wrap up with that. When you look at what SolidFire is trying to do here, it's really about delivering storage that is a better match for the type of compute that's going on in the cloud today, enabling more applications to move to the cloud than are running there today, allow service providers to manage and automate their storage environments like they do their compute environments, and do it all with a level of performance, efficiency, and cost that is very friendly to the service provider's business model and allows them to have a very profitable, successful service on top of this. So I think that's it for the presentation. I do want to get to a couple of the questions, and I've got some of them in front of me here. I'm not sure if any of these have been replied to in text, but I'll try to run through them quickly. And Jay, if you want to jump in on any of these, you can certainly do that.
Yeah, absolutely. You know, we've been answering most of the questions as we go along. There is one that I think didn't get answered yet, which talked about node failure. So why don't we, if you would, we'll talk about that. And the question was, what happens if we have a node failure within the system? Is there a degraded mode in which the system operates? And maybe you could talk a little bit about how the system then recovers.
Yeah, certainly. That's a great question. So the high availability technology we have has the ability to survive both disk level failures as well as entire node failures in the storage cluster. So what happens when that occurs? Because we use a distributed replication-based approach to redundancy, when a node goes away, we have redundant copies of that data located other places in the cluster. And what we will then do is redirect the I/O that's coming in that would be going to that node to those other locations in the cluster. Now, because of the way we distribute the data, that load is distributed very evenly among the remaining nodes and the remaining disks in the cluster. So rather than a mirroring approach where a single disk or a single node would now have twice the load to bear, and obviously a significant reduction in performance associated with that, the change in performance would be proportional to what actually failed. And so, for example, if you lost, say, one node in a, say, a 50-node system, you've really lost about 2% of your performance and capacity as a result of that failure. And what we're actually going to be doing, we redirect the, obviously, running I/O to the remaining nodes, but in the background, we actually rebuild the data that was lost. We rebuild that redundancy through the remaining nodes in the system, and again, rebuild it in such a way that we're not rebuilding into a dedicated spare drive or spare node. We're actually sharing that data throughout the remaining nodes in the storage cluster, and doing so in such a way that each node only has to exchange a small amount of data. So again, in a 50-node environment like that, where one node goes down, each node is basically sending and receiving about 2% of its data, which is a relatively small amount and can be done very, very quickly given the SSDs and the interconnect that we have. And so that impact in terms of overall performance impact is very small, and that rebuild time can be completed very quickly, and then you're back to essentially a fully functional system with no kind of negative impact or performance benefit, and you now have the ability to sustain additional failures without any impact on the system as well.
Super. That is great. So there's one other question we wanted to get answered, and then what we're going to do, folks, is just open up the lines, and we can let you guys ask questions live if you like. The other question, Dave, was centered around the type of workloads that SolidFire really excels at. And I thought if you could touch on that a little bit would be great for the group here.
Sure. So that's a good question. The interesting thing about SolidFire is we really have not optimized the system for one particular type of workload. So really what we've looked at optimizing for in the system is mixed workloads. For environments where you have a heterogeneous mix of workloads and application that you're looking to do. I think for any one particular workload, you may be able to build or find a storage system that might be a little bit more optimal for that workload. But when you have a wide range of workloads that you're looking to serve, say a mix of OLTP database applications and data warehouse applications and NoSQL applications and virtual machines and mail servers and file serving, when you have that type of I/O mix, that is, I think, where we excel the most. Now, we certainly will do well in individual categories in there. Certainly, random I/O we are very, very good at. We're very fast at. Database-type applications that drive a lot of random I/O tend to perform very well on our systems, and I think we'll be releasing some benchmarks publicly in the near future that illustrate some of that. But at the end of the day, I think if you look at what we do best from a performance perspective, it's really being able to serve a wide range of applications, to dial in the performance criteria for each of those applications around what that application requires, and to be able to do all of that at the same time on a single storage system, rather than have to deploy specialized systems for each different type of application in the cloud.